So the technique here is called partial expansion. And from our differential equation when we were solving it, that mass spring damper system, we ended up with this answer. And we want to get the time domain solution, x of t. So that means we need to inverse Laplace that. So we would go to a table maybe and look this up. But not all possible forms can be in a table. The table would be so big that it'd be unusable. So what we do is we decompose this into simpler forms that we know are in the table. And the idea is that we say, okay, we can write this as a bunch of products in the denominator. And the idea here is, this is the reverse of finding a common denominator. So we all do this, right? You can find a common denominator, which means you multiply 2 times 3 times 4. So that's 24. And then you multiply the top and the bottom to get 24 all in the bottom, right? So let's see. 2 times 12 is 4, so you get 12 24ths. 3 times 24. So that one's this. And then 4 times 6 is 24. But check me, make sure I'm doing this right. Does that look right? Yeah, so then you get 26 24ths is the answer, right? Well, what we're doing here is the reverse. We're saying we can write this thing in some of terms that are the products that make up the bottom, the denominator. So we're going to use the quadratic formula to find the roots of this thing. So that we can write this. In other words, we're just going to factor that, and it turns out they're negative. So the roots of s squared plus 12s plus 25, if you use the quadratic formula, or your calculator or MATLAB or whatever, you find out that the roots are minus 9.32 and minus 2.68. So that's what goes in here. Except we have to flip the sign because the roots are what make those factors 0, right? Does that make sense? Like if I plug in 2.68 here, minus 2.68, this cancels out and we get 0, and that's what a root is whatever makes that 0. And so then we look at this and we say we can split it up, again going backwards with the common denominator thing, we can split it up into something over this, something over this, and something over this. And then we know those are in the table and we can look them up. Are you guys caught up here? Good. And so we're going to write x of s and we're going to write it as something that we need to find, and we'll call this K0. I flipped the order here, but it doesn't matter. All right, so I need to find K0, K1, and K2. And there's a bunch of different methods. So you guys have done this before. How did you learn to do this in differential equations? Or do you remember? I know it's been a while. In Calc 2? Yeah, it's exactly that. One method is to simply multiply both sides by this entire bottom, and then equate equal powers of s. And we'll do that later, but there's a quick and easy way if you have these real simple roots that are not repeated. Like all of the roots here are different. The root here is 0, this is -9, this is -2. If you have all different roots, there's a real easy to find, a way to find like K0. So to find K0, we multiply by the thing that's under it. And then we let s go to that root that goes with that one. All right, so the s equals 0 root goes with that factor. So if we multiply both sides by s, multiply that by s, here we get K0, and then we get s times this, all of this stuff. All right, so I just multiplied by the thing in the bottom. And now we let s go to 0, and you can see how that's really nice. Here we've knocked this out. So letting s go to 0 doesn't make this go to infinity because it's in the bottom, because it cancels out. And s going to 0 knocks all that stuff out. And so it's really easy to find K0 because it's all isolated over here, and it's all right, so I stick in 0 for s, and I find out K0 is equal to, if you work all this stuff out, it's equal to 1. And we can do the same thing for the other two. And you can see that this works because there wasn't a repeated root like s squared, where we would have had an s in the denominator over here, and that would have caused problems. So we can find K1 the same way. We multiply both sides by this thing. It knocks it out over there, and then we let s approach negative 9.32. And you'll see why that's important to do. It's the same thing that's going to happen here. So to find K1, we multiply by s plus, that's the 9 point, right? The 9.32. And then let s approach the root that's going to knock that term out. So then we're going to get 25 over because we knocked out the 9.32 term. And I grouped these two together now because we're multiplying by this. I just moved those over here together. So I could do this. And notice that isolates K1 all by itself, and you can find it real easy. because as s goes to negative 9.32, that goes to 0. And we get 9.32 here, and we get K1. All right, so I'll give you guys a few minutes to find K2 the same way. Multiply both sides by the thing in the bottom. So we multiply by that and let s approach minus 2.68. So you guys are going to find K2 just to practice. Somebody on Zoom has minus 1.405. Anybody else? You got that? You got that? Some people here have gotten that? Yeah, that's right. I got 1.404, but I must have rounded something differently. So what that means is that now x of s, K0 was 1, K1 was 0.404, and then there's the one we just found. And so that's split up, and then we can look up each one of these in the tables really easily. In fact, if you split it up into this kind of stuff, real soon you've memorized that, right? This is the unit step, and this is e to the minus the number that's there. In fact, if you memorize just a couple of these, you can pretty much do any problem. So if we do inverse Laplace from the tables, then x of t, again, because of the theorems, we can go backwards term by term. This becomes the unit step. This becomes the exponential. And that becomes an exponential. And that's the same solution that we got last time for this problem using the traditional differential equation methods. So you can see that it's harder and easier than the standard method. What's easier is getting to this point, or the Laplace version, not the separated out version, because that's just Laplace and you're done. You don't have to think, well, what's the particular solution? What's the homogeneous? But you got to go through this partial fraction expansion. Excuse me. And what we end up with is this solution that's transient. And this is the steady state. And again, let's connect that back to the physical system. The original problem that we did last week, we started on mass initially unstretched at 0 velocity. And then we turned the force on at time 0 of 25. And what we found from the differential equation solution and from this is that it slides over and it stops 1 meter over. So that's the 1 here, this steady state solution. And the sliding over is the transient part. And those correspond exactly to what in the differential equation method were the forced or particular and the homogeneous solution. So you get the same answer because it's just a different way to get to the same answer, the unique solution. We'll do a few more comments about Laplace's later on. Let me make sure everybody's caught up on this board. An issue comes up if, let's say we s squared there, because we have to put an s squared here. But because there's actually 2 roots associated with that, there's s times s, it turns out to get the common denominator thing right, we've actually got to have one of these like as well. We've got to have all of the lower powers of whatever's there when you do the partial fraction expansion. And then if we multiply by s to get that one, it's going to cancel one of those. But then if we let s go to 0, it's going to blow up. This k0 over s blows up. So if you have multiple powers of the same thing, then you can't use these techniques to find those coefficients. And I'll go through an example of what you do then. The other way is to multiply by the denominator and then equal powers of s. Do you remember doing that? Because I think that's, in the past, students have said that's what they learn in differential equations. Because again, it's real straightforward. You don't have to think, you just do it. All right, so the big deal we get out of this for dynamical systems is we want to look at the roots or the eigenvalues of that denominator polynomial. Because in truth, we don't have to do the partial fraction expansion. We could look at those and we know what the response is going to be like. So let me show you how that works. In the solution we just did, we had terms that were e to the minus 9.32t and e to the minus 2.68t. And we said as time goes large, they go to 0. And it's because the roots are negative. And once we realize that every time we do another differential equation, if we get all negative roots, it's going to damp out. It's going to go to 0. And we're always going to have a steady state solution, and it's always going to damp out to it. So we learned that we can actually just look at the roots before we do the partial fraction expansion, and we know what the response is going to look like. For example, let's say we had this. Let's say we got minus 9.32, but we got plus 2.68. What's going to happen? Time gets large, that goes to 0. What's this? Blows up, right? So immediately we don't have to do the whole partial fraction expansion. We say, oh, positive root, unstable, it blows up. So you know that right off the bat. Sometimes with polynomials like s squared, let's say we reduce the damping to 6 in that polynomial. So this is b here. Let's look at that. Because we had b equal to 12, and we got those roots. If b reduces to 6, we've cut down on the shock absorber, the damper. What happens? I want to leave that there. No, I don't. Never mind. So what 12, now we're going to say, how about 6? So the differential equation looks like this. We could go through all the steps we did before, so that they're the same steps. All we did was change that number, right? And so we end up with a polynomial that is s squared plus 6 instead of 12 plus, and that's the characteristic polynomial. Just so to find the roots that we'd use in a partial fraction expansion, we set that to 0 because we're just going to factor it. We're going to factor it into something times something, right? And so you guys find the roots. I'm going to make you work today. You have a calculator. You can probably do it in 13 seconds. So I'll give you 59 seconds or less. I want the roots. Yeah, that's fine. Yeah, because, I mean, polynomials can have imaginary parts, right? Like if we have s squared plus 25, you get square root of negative 25, right? So you get, did I do that right? Yeah, go over the other side is minus, yeah, so you get plus or minus 5i for that. Yeah, so yeah, it can be real or imaginary or complex. That's probably what your calculator is giving you, right? Oh, it won't do that? Yeah. So some of it, I mean, a programmable calculator, or just the TI whatever will do imaginary, right? Oh, really? Let's see if we've got it on here. Yeah, so somebody on Zoom, -3. So minus 3 plus or minus 4i, right? So we got s minus 3 minus 4i and s minus 3, s plus 3 plus 4i, right? Because we stick that in there, yeah, then it cancels out. You guys know how to do this in MATLAB? Well, yeah, it's pretty much is. Let's do that real quick. Yeah, pretty much anything you want to do in math or engineering or science is somebody's wanted to do it before, and you can do it in MATLAB. So in MATLAB, you define your polynomial, p, and you do that as a vector, and you just give it the coefficients. So we have 1, 6, and 25, right? So the brackets, I'm making you remember back to 227, right? So you give it a vector that's the coefficients of the polynomial, and it just stores it as a vector. But then when you say roots of p, it goes into an algorithm and it grabs those coefficients and says, okay, they're a polynomial. Look, we got it right. So then what do we do with this? It means that in our solution, when we do the partial fraction expansion, x of s is going to turn into, we've got this polynomial, it's 25 over, we've got the s there, because that's the input, the force, and then we've got s plus 3 minus 4i and s minus, or s plus 3 plus 4i. And then that's what we split up into the partial fraction expansion. See what we did? I mean, these are the roots of that polynomial that was in the denominator of the transfer function. And so we split this up into, and we're not going to get the same numerators because we got a different thing in the denominator. And you could do the same process. You multiply both sides by s, evaluate at s equals 0, multiply both sides by this, and you realize that, gosh, keeping track of all the real and imaginary parts is a pain in the rear. And it is. And so when we get imaginary parts, I'll show you how you can look that up in the table. We'll do that in a little bit. But let's not find the coefficients right now, because what I want to show you is, well, what does the response do now that we've changed to b? Because now we've got imaginary numbers, and what do they mean? Before we had minus something, and we had minus 2. What's going on with the 4i? What do we do with that? So let's do the inverse Laplace. Oh, wait, I need to write it split. No, we split it up. Okay, so I'm just going to leave the constants there and say, okay, we'll find them in a minute. So we still get the step function from the first term. And from the second one, we still get that number from the root times t, because that's just a number. It doesn't matter whether it's real or complex. Look that up in the table. What did I call that? K2. We called that K0, K1, and K2 before, right? So there's my two roots. They're just complex rather than real. That's okay. The Laplace transform tables still work whether it's real or complex. And we look at this and we go, well, what does that mean? What does the response look like? Because now we got imaginary numbers in there. Before we said time gets large and those exponential terms go to 0, right? Well, what happens to e to the 4i as t gets large? Or what is e to the 4i? Yeah, it turns out that that is a sinusoidal. So that's where we're getting to here. In fact, we can make things easier because both of these have e to the minus 3. So we can stick that out here. And then we have to look up, go back and do a Google search or look up the math definition of what is, and I usually write it as theta because it turns out it's an angle. You write e to the I theta or e to the theta I. What is that? And the math definition of that is that this is cosine theta plus I sine theta. And it's not really a definition. It turns out if you do the Taylor series, the Taylor series of this and the Taylor series of this, and add them together, you get the Taylor series of that. And that's how it's proved. But we're not going to do that. We're going to trust the math guys. And so what that means is that this is sines and cosines of 4t. All right, theta is 4t. Here, theta is minus 4t. And so now what does the response do? It's the same problem. We put the force on at time 0. The mass is going to move to the right. But what does it do? Does it look like it's going to damp out to that steady state position of 1 here? Eventually. And what's driving that is the real part. Right? As t gets large, that's going to go to 0, and it's going to damp out. But how it gets there is different because now we have cosines and sines of 4t. So what do these terms do? They look like sines and cosines. Let's just do the sine one. All right, the sine at time t equals 0, sine of 0 is 0. It's going to go up to 1, it's going to go down to -1, and then after a period, it's going to go back to 0. And what's the frequency? The frequency comes from this number that multiplies t. So in one period, theta goes from 0 to 2 pi. Because it's an angle, that the sine and cosine are of angles, right? So what that means is that this number here is radians per second because what's inside the parentheses has to be an angle. So 4 is the frequency in radians per second. Or if you want to think about it in terms of the period, what we're saying is that one period has to match 4 times the total time. Why? Because one period, this whole thing inside here goes from 0 to 2 pi. And so 2 pi has to match the 4 times the capital T that got us there. And so from that, you can see that the 4 is a frequency as well, because it's 2 pi over the period. Again, radians per second. So what that means is that this part oscillates with a frequency of 4 radians per second. or you can divide by 2 pi and get hertz. And so now we have new rules or new insights into what the response looks like. This says that the response of the total system starts out at 0. I'm going to switch over here. We're about out of time, right? Oh, we got a little bit. Good. So the response of the system, x, the whole deal, is going to go up to that steady state position of 1, because that e to the minus 3t goes away, goes small. And so it starts out at the initial condition of 0, and it rises up and overshoots, the mass overshoots, and then it oscillates. And because of the e to the minus 3t, it damps out, and then the frequency is 4 radians per second, or the period is 2 pi over 4. So it takes that much time to go one full cycle back and forth with the mass. Oh, I didn't switch. Yeah, sorry. Thank you. Yep, I'm over here. Sorry, guys. And so now it becomes really easy to actually shortcut the whole process of doing the inverse Laplace transform, because we can say, let's look at the roots. We're going to look at the real part, and then we're going to see if there's an imaginary part. And this is now talking about the definition of dynamic stability, also tied to static stability, is we're going to say if all roots have negative real parts, all those come out here, they're e to the real part times t. If all of them have negative real parts, then the system and damped. And it's non-oscillatory. And if all roots have negative parts and non-zero imaginary parts, then it's still stable because we got negative, every one of those is negative. It's stable, it's damped, but it's oscillatory. Let's see, I should have set up here and 0 imaginary parts for this. So you can see how, if you remember this, it's real easy to say, well, here's what the mass does. Negative real parts, it's going to slide over and stop eventually. Is it going to oscillate? I look and see, do I have imaginary parts in any of the roots or not? And that tells you exactly. If any one of these roots, go over here, so if one or more of the real parts are 0 and the rest are negative, then what does that mean? What that means is we have e to the 0t. It doesn't blow up, but it doesn't damp out. And so we call this marginally stable. This would be like CG, we're at the neutral point. in pitch, well, it's not unstable, it's marginally stable. So this corresponds to that. And this doesn't matter whether we have imaginary parts or not. It can oscillate. If it's oscillating, it'll just keep oscillating forever. No damping. And then if even one real part is positive, then it's unstable. Because we have e to the plus 3t or something like that, and that blows up. And the really easy way to do this is to not remember this list at all. Simply plot the roots on the complex plane. Not an airplane, but a complex plane. And we'll start with this next time, but I want to introduce the idea. So here's the real axis and the imaginary. And you've done this in calculus, right? Where you plot the real part on the horizontal and the imaginary part vertical. You haven't done that? Okay, well, you can do it, right? Because you just plot 3 on the real axis and 4 on the imaginary axis, and that's what you do. So let's say we have all roots have negative real parts, 0 imaginary parts. So we're going to do, we'll call this blue. Where are those roots? They all have negative real parts. They're on the left side, and they have no imaginary parts, so you get 2 roots here. For example, we have like the, let's do this one over here. This is minus 9.32, was it? Those are those 2 roots we got when we had the damping of 12. Look at them. Yeah, they're both on the left side. It's stable. And they're both on the real axis, no imaginary parts, and it's non-oscillatory. See how easy that is? So really, this is the best way. Give me one more minute, actually 30 seconds. So how about this second part? We'll call this the green. Non-zero imaginary, but negative real. So that means we're like this. And you look at that and you go, it's on the left side, it's on the real axis, so it's oscillatory. And then last thing before I let you go, how about this one positive real part? That means you've got one over here, and then maybe one over here. You look at that and you go, that one over there to the right is positive. I'm going to get e to the 5t. It's going to blow up. Shows up on the right side. It's everything's on the left, then you're stable. So next time I'll show you what happens if we try different values of b. And we do this kind of a plot to see what happens. And like anything in math, this gets a little abstract, right? Because suddenly we've gone from a mass spring damper system to just looking at real and imaginary numbers. But you connect that to the dynamics and it becomes really easy to see, well, what is your response of your system?